We studied before inferences about two population proportions, and now we're going to discuss the inference about two means for independent samples, of course. So we're going to test hypotheses regarding the difference of two independent means and construct and interpret confidence interval regarding the difference of two independent means. The process is going to be similar to the process we followed when we did the hypothesis testing of two population proportions. We know that the sampling distribution of the sample means follows the student t-distribution. The sample distribution of the difference of two means for independent samples with population standard deviation unknown. This is Welch's t-distribution. Suppose that a simple random sample of size n1 is taken from a population with unknown mean mu1 and unknown standard deviation sigma 1. In addition, a simple random sample of size n2 is taken from a population with unknown mean mu2 and unknown standard deviation sigma 2. If the two populations are normally distributed or the sample size are sufficiently large, that is n1 is greater than or equal to 30 and n2 is greater than or equal to 30, then we can say that the t-score is going to be x1 bar minus x2 bar minus mu1 minus mu2 divided by the square root of the sample standard deviation squared divided by the sample size of the first one plus s2 squared divided by n2. Approximately, this follows the student t-distribution, with the smaller of the n2 minus 1 or n1 minus 1 degree of freedoms, where x1 bar is the sample mean and s1 is the sample standard deviation from population 1, and x2 bar is the sample mean and s2 is the sample standard deviation from the second population. So now that we know that this follows the student t-distribution, that means we're going to follow exactly the same steps that we followed for hypothesis testing for one mean in order to perform the hypothesis testing for two means. To test hypotheses regarding two population means mu1 and mu2 with unknown population standard deviations, we can use the following steps provided that the conditions are met. First, the samples are obtained using simple random sampling. Those samples are independent. The population from which the samples are drawn are normally distributed, or the sample size is large enough, that is bigger than 30. For each sample, the sample size is no more than 5% of the population. We're going to first, in order to test hypotheses regarding the difference of two independent means, we're going first to determine the null hypothesis and the alternative hypothesis. There are three ways that we can construct the hypotheses. The first way is the two-tailed test. The two-tailed test, the null hypothesis is a statement of equality. The first mean, the mean of the first population, is equal to the mean of the second population. And we say the alternative hypothesis, we assume that we hypothesize that the first mean is not equal to the second mean of the population. This is called the two-tailed test. And we can have a left-tailed test where the null hypothesis is going to be a statement of equality, while the alternative hypothesis is going to be a statement of inequality with using less than. So this is a left-tailed test. And we can have a right-tailed test, which states that the null hypothesis is a statement of equality and the alternative hypothesis statement of inequality with mu1 greater than mu2. The next step, which is selecting the significance level alpha. The third step is to compute the t-statistic. Now this is the difference between the two means and one mean. The t-naught is equal to, for two means, is equal to x1 bar minus x2 bar minus the difference between the means of the populations mu1 minus mu2 divided by the sample standard deviation of the first population squared divided by n1 plus the sample standard deviation of the second population squared divided by the sample size of the second one, which is n2, which is approximately follows the student t-distribution as well. And the next step is to compute the critical value t critical. The t critical is going to depend entirely on alpha. whether it is two-tail test or right-tail test or left-tail test, and the degree of freedom that we're going to choose is going to be the smaller of n1 minus 1 or n2 minus 2. If the first sample size minus 1 is less than the second sample, which is n2 minus 1, then we're going to choose the first one. The t-critical is going to be computed. We can use Excel sheet in order to compute t-critical. To find the t-critical for two tails, there is a function on Excel that is called t.inverse.2t, two-tail test of alpha, that will ensure that we compute the two-tail test, the two critical values for a two-tail test. So this is how we're going to compute the critical value if we have a two-tail test. If we have a left-tail test, then we're going to compute the t-critical using t.inverse of alpha, comma, n minus 1. This is the smallest of each. This is the smallest degree of freedom from the two populations, of course. And the previous one is the same, so there is degree of freedom n minus 1 here as well. If you have a right-tail test, then the t value is going to be, or the t-critical is going to be t dot inverse of 1 minus alpha, comma, n minus 1. N minus 1 is the smallest of degrees of freedom for the two populations or the two samples. And we're going to reach one of these conclusions. If we have a two-tailed test and t, this is the t-critical, and this is negative t-critical, then if t naught happens to be greater than t critical or less than negative t critical, we're going to reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis. If we have a left tail test, then we're going to find negative t critical. And if t naught happens to be less than t critical, we're going to reject the null hypothesis. Otherwise, we're not going to reject the null hypothesis, or we're going to fail to reject the null hypothesis. If we have a right-tailed test, then we're going to compute t-critical. And if t naught happens to be bigger than t-critical, we're going to reject the null hypothesis. Otherwise, we will fail to reject the null hypothesis. We have also another approach, which is other than the classical approach, that we call the p-value approach. The p-value approach depends on the probability of t is greater than or less than t naught. Depends on the type of the test that we're performing. After we compute t naught, we're going to compute the p-value using the smallest of the degrees of freedom. So if we have a two-tailed test, then the p-value is going to be the area, 2 times the area to the right of t naught. So here is the p-value right here, which is shaded blue. We're going to find one of them. Let's say we're going to find this area and then multiply by 2. To do that using Excel, you're going to say this is 2 times t dot distribution of t naught, comma, the degrees of freedom. And this is the smallest of the degrees of freedom. If you have a left-tailed test, then you're going to compute it using t dot distribution of t naught, comma, the degrees of freedom. This is the p-value. And if you have a right-tail test, then the p-value is going to be 1 minus t dot distribution of t naught, comma, the degrees of freedom. So as you can see here, we're going to find the p-value depending on the type of test that we're performing. After you find the p-value using your favorite method, my favorite method is using Excel, and I showed you how to do that. We're going to use this conclusion. So if p-value is less than alpha, we reject the null hypothesis. Otherwise, we are going to fail to reject the null hypothesis. And then the final step is to state the conclusion. These procedures are robust, which means that minor departures from normality will not affect the results. However, if the data have outliers, the procedure shouldn't be used. Let's look at this example. A researcher wanted to know whether state quarters had a weight that is more than traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters and weight each one of them and obtain the following data. These are the following data from the previous example for the traditional quarters and the state quarters. We want to test the claim that the state quarters have a mean weight that is more than the traditional quarters at a significance level of 5%. The normal probability plot of state quarters indicates that the population could be normal, and the normal probability plot for the traditional quarters indicates that the population could be normal. Look at how the left whisker is approximately similar to the right whisker, indicating that the population is going to be normal for both state and traditional quarters. The first step is we're going to write the hypotheses. The alternative hypothesis states that the mean for the traditional quarters is the same as the mean for the state quarters, versus the alternative hypothesis suggests that the mean for the state quarters is more than the traditional quarters. The level of significance is alpha, and we need to find T naught. T naught is computed using this formula, which is x1 minus x2 minus mu1 minus mu2 divided by the standard deviation, the sample standard deviation, the square root of standard deviation 1 squared divided by n1 plus standard deviation of the second population squared divided by this n squared. So we computed T naught using the formula for T naught, and we found T naught to be equal to 2.53. Now we're going to compute the T critical. The T critical is T sub alpha, because this is a right tail test, so it's T sub alpha, which is equal to T dot inverse of 1 minus alpha, comma, n minus 1. In this case, n minus 1 is going to be 15 because it's the smallest of the degrees of freedom. And we're going to end up with the T sub alpha is equal to 1.753. Now, if we compare the test statistic to T sub alpha, we notice that the test statistic is inside of the critical region, meaning we're going to reject the null hypothesis that states that those averages are the same. So we have enough evidence to support our claim that the mean weight for the state quarters is greater than the traditional quarters. We can use the p-value approach in order to reach the same conclusion. To compute the p-value, we need to compute the area to the right of T naught, because this is a right test. So we're going to use the p-value is equal to T dot distribution of T naught, which is 2.53, comma, degrees of freedom n minus 1, which is 15. We're going to compute the area to the right of T naught, and you're going to end up with 0.01. Now we're going to compare this to alpha. Alpha is 5%. We notice that p-value is less than alpha. 0.01 is less than 0.05. So we're going to reject the null hypothesis based on that. The conclusion is we have sufficient evidence at alpha is equal to 5% level to conclude that the state quarters weigh more than the traditional quarters. Note that the degrees of freedom used to determine the critical value in the last example are conservative. The results that are more accurate can be obtained using the following degrees of freedom. So we can compute the degrees of freedom using this formula. But we're going to stick to our previous approach, which is using the smallest of degrees of freedom.